Good day, good souls, and welcome back to the Anti-Science Theory. So today I want us to go over a very important topic, um, a very nice one, if I'm being honest. I mean, it can seem quite daunting at first, but if you can just give it a try, and then just give it a chance, I promise you, it becomes quite easy as time progresses. But I'll try my very best to make sure that you by the time this video or by the time the series ends you will have gotten everything you need under chemical equilibrium in preparation for your exams. Right. So before I go over some things, just you know the drill. It's very important that I get feedback on what you guys think on this. That is in many ways. Your comments are very important to me because it tells me basically how much or how helpful this thing is to you as an individual. I mean, if there are any things I need to fix, I can only know that if and only if you guys can tell me what it is that I need to fix. But regardless of everything else, I think it's best if we can just get into the business of the day. Okay, so when we speak of chemical equilibrium, which is basically, I mean, so if you hear the term equilibrium, what do you think of? When we say something is at equilibrium, we are saying that by definition, what is chemical equilibrium rather? Chemical equilibrium is basically defined as they say it's dynamic equilibrium, where the rate of the forward reaction is equivalent to the rate of the reverse reaction. It takes you back to when you were doing rates of reactions, the topic just before this one. I spoke about the rates of reaction, how fast or how slow a certain factor, and in any factor that you decide to introduce can be temperature, concentration, what effect rather does that particular factor have on the rate of reaction? Remember, rate is the key word here. How fast or slow a reaction can take place. Whether you increase your temperature, what would happen to the rate of the reaction? What effect would an increase in the temperature have on the rate of the reaction, right? But in basic sense, chemical equilibrium is basically um, um, it is when the rate of the forward reaction is equal to the rate of the reverse reaction, right? So key points that you must understand here is that chemical equilibrium can only be attained or achieved in a closed system, right? So you must ensure that you have a closed system for you to have, well, for you to basically mention anything that has to do with chemical equilibrium. You need to make sure that you have a closed system. Now, remember in physics, we spoke of an isolated system. In chemistry, we speak of a closed system. One would assume the two are the same. I mean, if you think about it, an isolated system, in the most basic sense, is a system whereby there are no external forces, right? And with a closed system, basically speak of a system whereby it's isolated from its surroundings. So this word closed system basically tells us that our system is isolated from its surroundings. That is, neither your reactants or your product can escape or enter. So think of it as something closed in a box. That is your closed system. So I have my reactants, and those produce my products. So none of my reactants nor my products can enter nor escape, right? We enclose them in some type of a box. So we say that's like our closed system, right? It's like they're locked in, basically. So my reactants and products are locked in something where they cannot escape, nothing can escape, and nothing can come or enter, basically. Okay, so very important thing to remember. Chemical equilibrium can only be achieved in a closed system. You'd notice in exam questions where they would always give you a statement, and somewhere along the statement they would say to you, um, they would say something like a reaction of, let's say, the decomposition of hydrogen peroxide, for example. There's a reaction of a decomposition. There's a decomposition reaction of hydrogen peroxide, and that particular reaction is in a closed system. So they will always mention that that particular reaction or something that gave you in the paper is in a closed system. So that's the key point when it comes to chemical equilibrium. It must be in a closed system. Right. We then speak of, say, for example, I have a certain, any hypothetical reaction you may think of. Say I have the reaction of A plus B, and this forms my product AB, my product AB, right? So the product that I form is AB. Now, if you think about it, I am basically using my reactants to form my product. Pay attention to the terminology I'm using. I am using my reactants to form my product. So there would be a typical synthesis reaction. There was a reaction where I am forming the product, right? Okay. And if you notice something, as I am forming my product, remember you read a reaction from left to right, right? So from left to right. In fact, even in math in South Africa, we just look at things from left to right. So it's like on a Cartesian plane, you know that your x-axis, you look at your numbers from the left all the way to the right. So that's the same thing that we do here. So we're going to look at our reaction from reactants to product. So in that way, my reactants will move in that direction to form my product, right? And that is in the forward direction, right? So my reactants are being used up to form my product. However, similarly, it can be a way in which my products can be used to form my reactants. That is, in this case, if you notice this, okay, let me first write it the way I would write it initially. So I would have A plus B. Instead of going in the first direction, I go in a different direction this time. That is, my products are being used to go back into the reactant. So I am breaking up my product back into its original reactant. We call that a decomposition reaction. So I am breaking up my product AB into its respective reactants, that is your A and your B. So in particular, what we are saying is if I can have a reaction, so notice how this one is going in the opposite direction. So if the first one is forward, then this one will be reverse. What we're basically saying is that if I have a reaction that happens, that occurs, right? And in this reaction, I can go in two ways. The first way is I can form a product from the reactants, and the second way is I can move from my reactants and back into my products, right? That means instead of writing these things as two separate reactions, that is reaction one and reaction two, instead of writing this in two separate reactions, we can just combine these reactions. And when we combine these reactions, we need to make use of certain type of arrows that tell us that this reaction is a two-way reaction. And that is when we speak of a reversible reaction. So, in essence, if I decide to write this in one way, I will just say the reactants plus my products, sorry, my reactants will then produce my products. And if it can go one way, then it can go the other way around. These arrows here, ladies and gentlemen, these arrows here tell me more about what happens in the reaction. These tell me that this reaction is a two-way reaction. It can go forward and backwards. It can go forward and in reverse. And we call this type of reaction a reversible reaction. Right, I hope you are fine so far. So, what is a reversible reaction by definition? A reversible reaction, in the most basic sense, is basically when your products can be returned or can be turned back into. I mean, you can use different terminologies, but your products can be converted or turned back into your reactants, right? So, when we say in most reactions that we've always learned from the moment you started doing anything that has to do with chemistry from grade 8, till date, right? Till matric, you've been doing reactions, right? But you've always been having a situation whereby you look at a reaction in one way. That would be your reactants being used to form your products, but now we're looking at how it would look like when we can go both ways. I can go forward and I can go backwards. I can use my reactants to convert into my products. Similarly, I can use my products to convert back into my reactants. That is when we speak of a reversible reaction. It is a reaction whereby my products can be converted back into my reactants. Which one are you used to? Reactants form products. Now you've been introduced to a different one where we can go both ways, and that is I can go forward and I can go backwards. That is when we use these partial arrows there to represent a forward reaction, and at the same time, a reverse reaction. Cool. Now, I hope that was very clear. Now, like I said, chemical equilibrium can only be attained in a closed system. That is a very important point to consider. Only in a closed system. But what then do we mean when we speak of something called Le Chatelier's principle? Now, Le Chatelier's principle basically tells us Le Chatelier. I've always had trouble spelling this guy's surname. Um, there you go. Le Chatelier's principle. So Le Chatelier's principle basically, let me just add the principle. Principle. Le Chatelier's principle simply states that when I have equilibrium, when I have a reaction that is at equilibrium, right? When I have that reaction of mine at equilibrium, and then at some point something happens. What happens exactly? We introduce a disturbance. So we are just gonna have a reaction at equilibrium, and we decide to introduce a disturbance. When I introduce that disturbance, what happens? Equilibrium will say, no, 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 no. You found me at equilibrium and you decide to just disturb me on a random day. I will not let that happen. I will do my very best to turn back into the original form. You found me at equilibrium and you decided to just change me and the form I was initially in. I will not let you succeed in that. So, whatever you do, I will do the opposite. That is when that is what Le Chatelier's principle basically says. It says that when equilibrium in a closed system is disturbed, the system itself will reinstate or reestablish equilibrium by favoring the reaction that will counteract your disturbance. So whatever you decide to do to the system will reinstate. Remember, it was initially at equilibrium. You introduced a disturbance. Now, the best thing it can do is to counteract your disturbance by doing what? By favoring a reaction that will go against what you have done. So I have a reaction at equilibrium. You introduce a disturbance. The system will reinstate its initial equilibrium by counteracting your initial disturbance. So what it will basically say is, sorry, what the principle says is that if you have equilibrium in a closed system, when it is disturbed by any kind of disturbance, by any factor that you use to disturb, right? So if you have equilibrium in a closed system, the system itself will reinstate or reestablish that equilibrium that it initially was in by favoring the reaction that will counteract your disturbance. For example, let's say you decide to increase something. That is so it was initially at equilibrium. Then you decided to increase something. The system will say, you are increasing something. We will do the opposite. In order to counteract your increase, we will decrease. Similarly, if you decrease something, equilibrium will say, no, why are you decreasing? We want our equilibrium back. Therefore, instead of decreasing and going with you, we will counteract your decrease by increasing. If you decide to add something, the system will remove. If you decide to remove, the system will add. So everything that you do, every disturbance that you implement on a system at equilibrium, that system will reinstate its equilibrium by opposing or counteracting your initial disturbance. So in a nutshell, that is all that Le Chatelier's principle says in the most basic sense. You introduce a disturbance to a system at equilibrium, that system will be so stubborn to a point whereby it says, you know what, I will not let you succeed in trying to change my initial form. So instead of letting you succeed, I will counteract every disturbance you do. I will make sure that I oppose it. That is basically what Le Chatelier's principle says. Right. Okay. Now, what I need you to understand is that with chemical equilibrium, we have different factors that affect the chemical equilibrium, right? So the factors affecting chemical equilibrium. Factors affecting chemical equilibrium. So in rate of reactions, we had five, in fact, six factors. That includes the nature of reactants. And in chemical equilibrium, we are only going to use three from the five. The first factor would be your concentration. Now, what you must understand from rate of reaction that concentration only affects substances that are in solution, that is when you speak of your aqueous substances, and as well as your gases. No solids, no liquids, right? And then we speak of temperature. So temperature, when you speak of temperature, we speak about two types of reactions, right? Your exothermic reaction as well as your endothermic reaction. Exothermic and endothermic. And then the last one is your pressure. So pressure only affects gases, right? So these are all your factors that affect chemical equilibrium. So it's very important to not forget these. These are all your factors that you must remember when you speak of chemical equilibrium factors. Well, basically, those are factors that affect equilibrium position. But for now, we will leave the video here. And in the next video, we will dive deep into each and every one of these factors with proper, clear, and precise explanation of each so that you are ready for your exams. So it can be your June exams, your prelims, or your final exams. You need to make sure that you master this topic so as to make sure that you get total marks in this topic. But from me to you, I shall see you in the next video. Thank you for watching. Goodbye.